Okay, so your quality of call is amazing. Your video is amazing. Everybody should have in this modern world a high quality broadband. If you are going to be a professional, interacting with people around the world, you've got to get to wonderful. Invest your money in broadband, please. I know, if you invest in money, you can also do other things. Watch Netflix and so on. But I'm not going to enter the topic. Don't waste your time. You should enjoy certain movies, certain number of hours and so on. But more importantly, your world is opened up. When others see you and hear you very well, they give more time to you. This is not about me. I'm saying in general, you get better attention. So it's very, very important, Abhipriya. Make sure that you have a great, if not today, towards that goal, great broadband. Okay.
Yeah, sir.
All right. So I'm still waiting for Goshali. Goshali for Mallikarjun. Situation is not clear, but I'm going to start. Okay. Our times are very hard pressed, and I appreciate both.
Yes, sir. We can start.
Yeah. Thank you very much, Goshali.
Yes, sir, we can start.
We are hard pressed for time. In the sense, we continuously have to make sure that we are moving along in our course. There are some delays because of pandemic, but we'll be good. Okay, we'll be good, and we are going to have more activities in the institute. All right. So certain things I will not even bother to talk about it, like about me, because you know it. Otherwise, you probably you'll come to know of me later on here in this slide. Some other slides I will skip. Okay. So the first and foremost thing I want to tell you is you are able to see my screen. Okay. Let me make it a full screen. We call it as predictive analytics. Also, it is same as saying predictive analytics and supervised algorithm. Okay. By that I mean you have an outcome variable. You have an outcome variable. Note down this. Supervised algorithm means equal to have an outcome variable or labeled variable or labeled data. Okay, it's a very important definition, right? Supervised algorithm means it has algorithms where you have an outcome variable or or a labeled variable, or sometimes it's called labeled data. That means you have a labeling of the particular record. This record means tiger. This record means lion. This record refers to rabbit or things like that. So the record, each record of characteristics, attributes are referred to with a label. Okay. From the statistics point of view, it is called regression models and classification methods. Okay. So it is here as supervised methods. The regression models are classification methods. These are all definitions. You may be asked, sometimes in conversation or even in interview, they might ask you, oh, tell me an algorithm which is unsupervised. Which algorithm you like most and why, and so on, so forth, right? So sometimes you'll get a train sound. I'm sorry about that. I got to mute for a short while. Just wait 30 seconds. So in this, what you might be wondering, what am I going to get out of this course, right? This particular course. So you will be able to build, interpret, and implement regression models where the outcome variable is a continuous variable. Please note it down. Regression model is equal to a model where outcome variable is continuous variable. Continuous. That means, it's also called a ratio variable, right? You might have heard of it as ratio. Okay. That means, the values can change continuously. It's not a classified nominal variable. Okay. Yes or no, or no, A class A, B, C, and things like that. It is not. It is continuous variable. So you'll be able to build, interpret, and implement regression models for continuous dependent variable, whether it is 5 independent variable, 1 independent variable, or 500, 5,000 variables, you'll be able to do that. So what is meant by independent variable? Which means the variable that explains the outcome variable. Please write it down. Independent variable is equal to the variable that explains the outcome variable. Okay. Here you will be able to not only regression but also the classification model. You're able to do the above for classification models, which means you can work with qualitative data. That means, as I said, given the data, predict whether it is a cat or a tiger. Okay, it's a tiger baby or a cat baby, or lion baby. Things like that, So you will be able to predict classes also. That is called classification model. You'll be able to articulate why the created model cannot be further improved. Very, very important, which means that is the best model. Okay, you cannot improve anymore. This is the best model. You put a stamp. This is the best model as an analyst, and you'll be able to diagnose whether a model satisfies foundational structures. And it is important because if these foundations are followed, it is going to be of this estimate and it's a great model. If on the other hand, if the model has this kind of structure, it has these properties, it fulfills these properties, then it is a different type of model and this is the best model you can build. That's kind of argument you can make. Okay. So you will be able to create also predictive models when the dependent variable is not normal or logistic. So now regression is usually the variable is normally distributed. The outcome variable is normally distributed, and the classification model is usually the underlying probability distribution for the class variable is logistic regression. But sometimes you may face situations which are not normal logistic, but Poisson, negative binomial, gamma, and so on. So you all heard of these probability distribution names or not? Just heard of it or not? Just give me input. I constantly will ask you questions. You can type if you cannot talk. Try to do.
Yes, sir.
Abhipraya. Yeah, you did great, Antos. Thank you very much. Okay, I appreciate that.
Abhi ma'am and I had done the courses together right from the start.
Which
our courses?
Oh, I see.
The statistic. Yeah, the statistic classes as well as the R classes.
R program.
Excellent, excellent. So how do we do the models? Because there is so much work done, so much clarity, perfection established on the regression model with the normal distribution and logistic distribution. But then, can I achieve these kinds of things when the outcome variable is not normal but Poisson, or it is negative or gamma? Those are things also we will discuss, address that. So I want to attend to you some very classic examples. Okay. Sometimes you want to predict a newly born child's height, how much they are going to grow when they are born, not until you wait, they grow into. Okay, that's a very classic example in statistics. Why do we need that? Because they need to know, usually not as soon as they're born. I'm just saying, as the family grows into, the child grow into more and more ages, they still want to know whether they reach a certain predictable age. Okay, a father and mother on an average, if they have, for example, I'm saying if they have 5 feet and 5 inches, there is a worldwide population or even sub-segment wide population, because Indians 5.5, 5 feet 5 inches is different from thinking about an American or German or Chinese. Okay, so the point is sub-segment. They are called sub-segment. So given a sub-segment, we have understanding about where they should grow. If they are not growing, that means there are some nutritional issues, some family issues, some growth issues they have to attend to. So predictively, we need to know where they are going to grow into. Okay, so there are studies we have done, and we have built wonderful models with samples to predict these kind of situations. Okay, is the example clear to you? Some few examples I talked to you. You have to talk to me. Stop me, ask questions. I'm very happy to address. Okay, interaction is extremely important. Another example is I would say this is a very classic model also, house price model. Okay, it is common when you buy a house, whether you are paying the right price for the house. And house is the largest investment besides education. House is the largest investment people make. Okay, and even 5-10% variation can be huge. I don't know, sometimes $50,000. And I will usually talk in terms of the U.S. market and U.S. Prices, dollar instead of rupees, and so on. So please hang in and stay with me. Listen to me. Don't get distracted by those U.S. market, U.S. numbers, and so on. Okay? So one moment, I need to reduce some noise. Sorry about that. Okay, so so that's one of the examples we will talk about. How do we do that? This is a competition model. Actually, you will see it is following some best practices. You will achieve the competition level performance of the model. Okay. The third example I want to talk to you is, these are what are called shells. Okay. Some people eat this. They open it, they take the meat and then eat it. Okay. This is one of a delicacy in the world. People love to eat this one. But the problem is, for the farmer who farms these things, from the seashore, or even you can grow them in your own pond, or clean pond, or a lake, and so on. They want to grow this, but they don't want to open it before they give it to the consumer, before they sell it to the consumer. If they open it, but the consumer wants to get the best meat, isn't it? Healthy, nutritious, not spoiled meat, okay, not infected meat. So when the consumer wants to open it, but the producer don't want to open it, okay? Because if you give it healthy, unopened, then the consumer will pay more money, okay? So unopened. So how do we solve the problem? Do you understand the problem? Do you understand the problem, what I'm talking?
Yes.
Anto?
Yes, sir.
Yeah, you do. Okay. Abhipriya?
Yes, sir.
You can type, that's okay. Huh? I can't hear you. Okay. I can't hear you. No problem. This is a predictive problem. What is the prediction here? Is the meat of a certain quality. Thank you very much. Is the meat of a certain quality. Okay. So they will predict that. Based on that, they will price it. And when they open it, oh, this is great, as predicted, as committed, as suggested by the producer, it is that quality, because they can now price it at different level. Quality A, B, C, D, E. Something like that they'll put, right? The price between A to E could be huge. Okay, A could be probably, I'm talking about 5 times the price of E. So because it also goes with the assurance, because consumers in general are very picky, and if they don't like it, they'll say, no, give me the money back. You cheated me, right? So it is important to predictively classify these things as they, what is the amount of meat it has and how good quality that is. Okay, so we are going to predict that kind of problem. These are all some interesting examples of prediction. Okay, and here is another example, right? Keeping good health. You all probably know everybody wants to walk 10,000 feet, 10,000 steps you have to go if you want. The other problem, if you want to keep up your, healthy stature and the weight and the overall health of the human, the body, in addition to eating some good nutrition. Okay, so there is some prediction you have to do whether you are able to maintain your health, if you continue to do certain activities. And once it is validated, of course, everybody will follow that method, but still we have to see whether we can predict the good health based on certain activities, okay? Which is a very classic example. So predicting fat content, for example, in this case, of course, I also want to mention fat content. Fat body content is very, very important, because it reduces your energy level, it increases more comorbid situations. So it is important to maintain a right amount of body fat, right amount of protein, and other nutrients. Okay, and also sometimes even if you are sick, your treatment gets better effect if you maintain certain levels of these minerals and the nutrients. Okay, I think what happens is if I am in the full mode, the video goes on also. Okay, so that I was listening to it, so I realized. Okay, so this is about me. You can read that. I will give you this presentation deck. The other thing you want to think about is what is the difference between statistical learning and machine learning? Okay, it is the same thing. The only one big difference is machine learning, we are supposed to get automated feature selection. In statistical learning, statisticians think very carefully, spend a lot of time looking at the data, thinking about it, and then coming out with features. But machine learning will help you to solve that problem easily, automatically. Okay, whether that's the best thing or not is very important question too. See, machine learning depends on lots of data, and statistical learning, same thing, but probably a lot more models are not probably. In fact, more modeling techniques are available in statistical learning. The reason why statistical learning still is valid and important is that oftentimes you have to collect data very carefully. Machine learning is give me all data, I will do whatever you want, right? Attitude. Oftentimes that's a situation. So it's what I call it as, this is the statistical learning is a situation where you have to use designed data because you cannot collect a lot of data, point one. And the other thing is, you are so focused in your research questions, you want to address a very specific research question, a very specific output, specific interpretation, and so on. Okay, so in order to achieve that, you have to design the data collection. That means you are going to spend a lot of time and a lot of money, which is especially this is very important in health. Okay, where collecting data is not easy. Okay, so it's a designed process, and you need to still work with the limited data. There are a lot of situations like that. Okay, suppose you are estimating the universe, age of the universe. There are probably 40 observations or 50 observations. That's all. Okay, and with that you have to estimate the age of the universe. Means you have to use statistical learning, not machine learning. Okay, even though you can use it, but you can use both the problem. In machine learning, you can also use it for small data. But the thing is, typically we don't do that because we want the machine to provide the algorithmic steps to provide the automated features. Okay, but automated features usually may not work in the case of the very small sample sizes. So you still need to know statistical learning. By the way, I want to tell you a very important reference. You might wonder where to, for both the courses. In fact, yeah, for both the courses, supervised algorithm and unsupervised algorithm, I'll give you one reference book called, written by Tip Sharani, somebody. Okay, it's called Statistical Learning. Okay, that book is statistical learning, but he will include machine learning methods, also the boosting methods, and neural nets, deep learning, not deep learning, some other additional methods. Okay, but the point is, I'll give you that reference later. Okay, that's very important. So there are lots of different methods. We will cover almost all of them. Okay, quickly in the whole program with 3 courses with me. All right. How do we approach the course? Think different. Be problem focused. Create outputs for predictive purposes. Okay, we'll have to do this all the time. Questioning is important. Sometimes questions are more important than the answers. Okay, and you have to think different also. Don't accept, as long as it appeals to your logic, we are good. You are good, I am also good. But if it doesn't appeal to your logic, there is some bridge we have to build. Okay, and you should constantly seek consistency of interpretation, consistency of coming together of topics. They are, everything has to come together to some foundations. Okay, and so you have to be able to ask good basic questions that will help think independently. You as an independent human being. Okay, so you go down to the basics. So if something is not explainable, that means some basics is not fulfilled there, satisfied there. That is how you have to think. Okay, so we all have to commit to this. Ask why in addition to how. How is given us some data points, you build a model. Anybody can do that. In fact, AI is going to do. As we grow, AI will do whatever you are going to do as model. So that's not that great, but AI will have tough time. It will improve, but eventually AI will never be able to beat the why aspects of life, as the humans think. So there is the reason why you and I will continue to exist. This world is not going to be completely run by AI, okay, which is only artificial. It's not natural intelligence. So ask why do you have to care about this? Why do you have to do this stuff? Why not this way? Things like that. Very basic questions you have to keep asking. Go through hand calculations in the beginning and connect with structures of intelligence and data points. Think about this, structures of intelligence. Okay? That means there are different thinking patterns we develop on how to do things. Okay, and so we have to connect to those things. And in fact, when I said Poisson distribution and normal distribution, those are all different structures. Use graphics to explain and understand, to understand. Use R codes to run some simple computations. You use R to run complex competition level problems also, as well as actual industry problems. That's how we are going to. How does it sound? You're all ready? So okay, these are all these things you can fill it up yourself. List of topics we covered, list of data sets we covered, list of exercises we covered, list of assignments we covered. You fill it up yourself. Okay. So the earliest example is I would say this is the first example of predictive modeling. Okay, that happened approximately 160 years back. This is actually the handwriting of Galton. Okay, somebody called Galton. His last name is Galton. Maybe first name is Handley Galton. I'm not sure about the first name. Okay. So it was a handwritten note from 1875. Okay, 150, almost 150 years old, right? When statistics was born. So let's understand this data here. This is data for nutrition study. Okay, remember that first example, age prediction? That is it. It's about that. You are able to understand this is 18.5, right? This is 7.0. This is 13.2. These are all 60 plus. That's how you have to interpret. That means 78.8, 67.0, 70. This is 73.2. This is 69.2, 69, 60. So this is sun. Multiple numbers means multiple son, multiple. This means daughters. Multiple numbers means multiple daughters. So in this family, we have one father height, one mother height, and one son height, and 4 daughters height. You understand how to interpret this? Both of you? You just type it. Okay. Anthony,
yes, sir.
Thank you. This is very, very important. When somebody gives you data, you have to know how to read the data, how to interpret it. First and foremost. If you don't know, it's your duty to ask that, hey, tell me, how do you interpret this data? How do I read your data? Your data, right? You are an analyst, somebody is going to give it to you. But it's also possible they might say that no, it's your duty to read it. Well, who structured this data? See, this case, he is the data collector. Galton was collecting the data also. He is also an analyst, but he collected data. This is the This is where the statisticians differ from machine learning guys, right? Machine learning guys get the data. Statisticians sometimes they have to collect the data themselves. They have to think about it, how to structure data, how to, you know, how to collect, how to design the data collection process, and how do we record the data. All those things statisticians think about. Machine learning people, they don't have to worry about it. The data engineers will do that for you. And then they will give the data to you, and then you do this algorithms and so on. Okay, so there are some differences between the way statisticians work and the machine learning people work. Okay, but it is very, very, very important to ask a question about, tell me, you have to figure it out, or you have to ask others to help you figure it out. As a statistician, it could be more complex than machine learning, because data engineers will give you the data log or data dictionary they will give you, which means it explains all the data elements in what form, and so on. So, for example, it is very difficult to interpret this line unless somebody explains it, isn't it? Why it is, these are all inches, but there's an offset. The offset is 60 inches. So, that you have to add 60 to each of these numbers is an important information. Why 60? It could be 62, right? But somebody has to tell you that. Otherwise, you are going to go crazy, right? So, understanding data, please write it down. Understanding the data in terms of its structure, in terms of its interpretations, in terms of its units, in terms of its missing values, all those things matter. Okay. So there is, about 4.0, because they don't know exactly. And then there is a minus 1.5. That means 60 minus 1 point, right? These are things you have to understand. And these families don't have boys, only girls. There seems to be a lot of girls here, right? More girls than boys. And there are families where very few families without girls, but more families without boys. All these things are very useful information, very powerful information also. Okay, and without this, you can never interpret the model as you build. You can never be able to build the model also. So be careful about when you receive the data, you know how to read the data. Point one. Now, here is the question I have. Okay, suppose in your town, Anto, okay, or Abipriya, in your town, you are asked to tell what is, you randomly pick a child. Nobody tells you how old and so on. Okay, they don't tell you. You don't even know. You don't even know the picture of the child. But you are given a random sample. This is a child picked up from this in your town. Okay, but I give you, father's side and mother's side, and the question is now, can you predict the child's, ultimate height? Do you understand the question? And if you are asked to predict, what is the best thing you can do? Okay, let me say one more point here. So you have father side, mother side, and also all the collections of children in this. So father side, mother. Let's take this one, the one example we talked about, right? Here, right? So we got father side, mother side, and all these children. These are all grown-up children, actually. I think these are all grown-up children already. But what I am saying is, okay, so you have in your town, this is something like around 800 children. Okay, 800 children, and for each of the children, you have the father side, mother side, and their own ultimate height. Okay, so that is the situation of the data. But what I'm asking you to do is, you randomly select a child from this data, right? Randomly select a child. You don't know the gender, you don't know the height, but randomly select and ask you to predict a number. What would be the child's height? What idea will you have? Do you understand my question? And what will you do? How will you predict? Okay. Abhipriya, you can type if you want. Anto.
Sir, I've understood the question, but I'm not very sure about the answer. I can give it a try though.
Please do. There is, remember that there are no right or wrong answer. It's because it's just we are digging. Okay, right or right, wrong is not important, but we are digging. We have to try. Go ahead.
So the past data with the past data, the mother's height, the father's height, and the corresponding son's height or the daughter's height. Using that, we can use some multiplicative factor.
Multiplicative factor. Okay.
With which we can try to
multiplicative
predict.
factor. Okay, something you are going towards a regression. I don't want you to think regression yet. You are going in the direction of regression already. That's the multiplicative factor we are going to find. We'll come to that. Okay.
No, so actually, I did not try to go into regression. I'm not very sure about that too.
No, you are.
That is
I'm telling. I am interpreting what you said.
Oh, okay, sir.
Okay. You are perfect. What you are thinking, logical thinking is good, but I want to wait there. But the simplest thing is, okay, let's do this. Abhipray, do you have any opinion? You can type. Okay. The simplest answer is that, okay, I'll take the average height. How about that? Does that make sense? I randomly picked somebody, some child, grown-up child. We are talking about grown-up child. Somebody I picked randomly, and then I'll say, what is the height of that? What could be the height of that child? Means the average of all the children's height. That is a good idea, decent idea. Why? Because most of your observation is going to be near the average. Is it correct?
Yes, sir.
That's because of the probability distribution, right? If you plot the distribution, that's what this says. Most of the observation is around the averages, right? In this area. That's my average, median mode. Most of the observation. It's not going to be 80. It's not going to be 60. Most likely, it is around the average. That's a simple, good point. Good idea, right? But can I improve that? That's the first approach. The question is, can I improve? Basically, I plotted the Galton dollar height. Height means in this case children height. Okay. I do a histogram, and then I do also the probability distribution. Overlay that. Okay, using the line command, and then I say, oh look, mostly it is normal distribution, and it's okay if I say average. That's a simple, beautiful rule. The thing is, can we improve? That's the question. All right. That's the first question. The other thing I want to tell you is that the average is also, anything you take random sample, average approaches the population mean. So even if your population is 10,000 people, okay, and you take only 10 samples, the average average height of the 10 sample will be equivalent to, with probability 1, to the population 10,000 samples average. That is what is called the central limit theorem. Okay, so average is a good estimate that approaches the population average perfectly well. You can't beat it. A very simple solution, it works. I want to tell you another important statement. Statistics is the science of approximation. Please write it down. Statistics is the science of approximation. It's not about perfect statement. So that's why I said most of the observation will be around mean. That's all we need to make sure. It may look like, oh my goodness, the science is made very simple. Yeah, because it's so complex, we try to make it simple. But you shouldn't fall into the trap of that and then try to make too simple. Then you will fail in your prediction. That's why we need a science. So it's called statistical science. It's not it is still a science. All right, but very important. It is all about statistics is about approximation, and it is about most likely value, most likely estimate. Sometimes we call it maximum likelihood estimate. Okay, most likely. Please write it down too. Statistics is the science of approximation and the most likely estimate. Okay. So the question I asked is, no, can you improve? Let's think very deeply about it. How can we improve the estimation that we said? The average is the best estimate. Can we improve that? I have father's height, mother's height, and the children's height. I randomly select somebody, and then I'm trying to predict that child's height. And the first solution is, put anybody you pick, you say average. Okay, that works, but can we improve? That is a question. Any idea? You have extra information. What is that information? Father's height and mother's height. That's extra information, isn't it? Because taller fathers are going to get taller kids, and shorter fathers are going to get shorter kids. That's the biology. There's nothing wrong with it, isn't it? So can we use that information to improve the prediction? That is the question. Okay. So answer is yes, because we know that taller fathers are going to get taller kids. On an average, shorter fathers will have shorter kids. Of course, you don't have to stop with that. The combination of taller father and taller mother will have a different impact compared to combination of taller father with shorter wife, shorter mother. Am I making sense? It will have a different effect, isn't it? You can put yes or no.
Yes, sir.
Yes.
I watch in the, you can say loudly yes or no, or you can type. Okay. Are you with me, Habipriya? What I was saying. Okay, excellent. So that means you are bringing two factors into the prediction, but let's wait for that. Okay. Just let's use father's height to improve children's height, the prediction of children. So I'm going to copy and paste this, one second. These two codes. You can use these codes to immediately, both of you should, fire the R. You have R that you can use it. Please, so, start your R. I'm going to start R. Okay. And I'm going to paste you this data. If you click on this, you will see the data. Okay. This is the data that we are going to use. If I click on it, you see this one? This is the Galton data. Same thing in the book. What I read is here. Okay. I added one more column. How many kids are there? But I didn't take, I wrote the data in a different format. This is called long format. Okay. Both of you understand what is meant by long format? That is a short format because one line has 4 records for the first family, right? That's what this is. This is the family number. One line had 4 records. I spread it out into long format. It's called long format. Both of you understand what is meant by short format and long format because we will use this kind of terminologies in our profession.
Yes, sir.
Thank you. All right, so this is the data. Let me also give you the codes to read that data into R, okay, quickly, and then check some sample information. So that is the data. Sorry, I didn't put that until now. So you have to define that ID is this. Okay, so just copy and paste this part alone in R. So I'm going to do that now. Go back to R. And I'm going to say start a new one. Let's start a new one. Just I don't need to start a new code book, but just type this one. Control V. Okay, there you go. Are you able to see this one? Are you able to read, or you need to want me to make it bigger? Global option. Okay, let's see. Appearance. Okay. Now you are able to read better now, isn't it? Is it good enough for you, Abhipriya? Is it okay, or you want it
Yes.
bigger than this?
It's visible.
Huh? Anto is okay?
Yeah, it's okay, sir.
All right. So what did I do? I put the link, say a specific part of the Google file into ID, and then use this command read.csv sprintf that Google ID here, and then export is equal to download ID. Okay. Head, so head for me is 5 records, so that's what this one is. So it is in the long format now. Now I have read it, I can do whatever additional computations I want. But where I went was with the idea that it is important to see whether I can use other factors to explain the prediction. Okay, average is one of the best possible centrality of distribution observations. The other are median and mode. Okay, they are also talk about the centrality of the distribution of observations, the location of the distribution of the distributions. Okay, and besides centrality, in general, we also want to know how dispersed the data are, how much widely distributed, because the more tightly distributed, more easily predictable. Your predictions are more accurate, more often accurate. So dispersion is also important. So centrality or location and dispersion are two important fundamental concepts you have to use to predict better. We also want to know how they are skewed, left side or right side, how tall, lanky or flatty, all those things are also important. But I'm just building little by little. Okay, most important is location and dispersion. And if you're looking for some specific cut points of accumulation of ranked observations for below some cut point, percentiles and quantiles are very useful. Okay, so if you are looking for I want below this cut point, what percent percent observations are there, and above that cut point. So whatever the cut point, any cut point here, you select and you try to find out what percentage is above, what percentage is below. Then we are talking about percentiles. Okay, so these are general quantities you want to really understand about distribution, probability distribution. That is location of the observations, and then the dispersion of the observations, how skewed left or right, or how tall, lanky or flatty in relation to normal distribution. All these things are in relation to normal. So normal distribution is your standard. You compare that to make such statements. Okay, if you are looking for specific cut points of accumulation, we talked about that. Also by central limit theorem, the mean always converges to the asymptotic normal distribution under very large collection of situations, very robust collection of challenges, it satisfies. Okay, making average or mean as a very desirable measure of central tendency and usable estimate. However, we should always be open to use a right measure of location. Okay, remember, sometimes you may want to use median, sometimes you want to use median, mode, or mean. Okay, so but using under what conditions what is also important. Those are all covered in statistics, but I'm just quickly reviewing it because we want to take the knowledge from those things to come back to our sole purpose of prediction. Okay, so here is the reason why using additional factor can help you. Okay, I said father's IP are going to use. So here is a very simple 4 observation situation. Okay, so if I have average income of people is for 50,000, and average income of males is 60,000. Okay, yeah, these are the 4 samples. Let me go back 2 steps. So here I have 2 females, salary and 2 males salary. Males get 70,000 per year. First male, the first female gets 30,000 per year, and second female gets 50,000 per year, and second male, which is the 4th observation, shows getting $50,000 per year. So in this case, the average of all these 4 people is 50,000, isn't it? So if you randomly select somebody's, somebody here and then ask what is the best estimate of their income, you give the 50,000. Okay, because one estimate only I said, we don't know whether it's male or female. If I put that kind of question, you will say, excuse me, sorry. You will say 50,000 is the annual income of anybody randomly chosen per year. But if I say no, I want I know the randomly selected person is a male, then you will take the mean of these two people only. I'll say, oh, it is 60,000, isn't it? Am I correct? If I say that additional information that the selected person is a male, then you will say take the average of males alone and then say it's 60,000, not 50,000. On the other hand, if I say the selected person is a female, then you will immediately calculate the average of those two female and say, no, it is 40,000. Isn't it? And those are the best answers, isn't it? Because of the average is the best number when you don't know the specific person's information. That's the best predictor. And what we did in this simple example is that by using an additional factor, that is the gender information, you are able to predict better because the 60 is closer to 70 as well as 50,000 for the males, and 40 is closer to females, for 30 and 50,000. So your prediction is more accurate because you used that extra factor information. Factor means in this class, male or female gender, that extra information. And what you also did, listen very carefully, what you also did is you took conditional expectation. So when you have additional information, your conditional expectation is your best model or best estimate. Please write it down. When you can do conditional expectation, that is your conditional average, is same as conditional expectation. Conditional average or conditional expectation is the best predictive estimate. Did you get it? That's an extremely powerful statement. It looks like a very simple statement, but it's extremely powerful statement. The whole prediction is about conditional expectation. Okay, so that's what graphically I'm showing you. See, all these people are individual data points. Okay, and blue refers to males conditional average, conditional expectation, males conditional average. Conditional average means you are conditioning on the gender, and the purple or pink, not purple, pink is refers to conditional average of females income. Okay, and you see how different they are, and because you used, otherwise you would have taken only black estimate, that's a middle point, as your best estimate. Because of the extra variable, extra indicator variable, extra qualitative variable, that is the gender, you are able to predict better because you separated out more relevant information for that. Separated out it, and then you use the conditional expectation, conditional average, conditional mean. And it is always true. And that is what this formula says. Okay. It says this is the most important formula. It looks very complicated looking, but I'll explain it to you. The variance in the outcome variable, the total variance in the outcome variable, can be split into two parts of variance. Okay, one is average of the conditional means variance, right? Average of the, we'll call it as the average of the conditional variance plus variance of the conditional expectations. There is a mathematics that we can figure it out, but don't worry about it. Most important thing is your average. This is the actual average, actual dispersion in the original data without conditioning information. But because variance is always positive, this is positive, this is positive, this is positive. So this, if you remove this one, variance of the conditional expectation, and this one is, or you remove this one, this either one is less than this one. So what we are saying, this is what the predictive error. This is the second part is called the predictive error. So let me write it down. It will help you. I should do that. So this is two parts, right? The total variance is equal to. It's coming, one moment. Total variance is equal to total variance is equal to average variance of average conditional variances plus variance of conditional expectations. Okay, so what we are saying is the variance of conditional expectation. Because this is a positive number, if we take this, what does this mean? That means this has to be less than this. That's what it means. It's a positive number, it's a positive number, it's a positive number. So this will always be expectations. Okay, this will always be less than this one, which means what? The prediction of using conditional expectation is better. It has less uncertainty. Variances means it's a measure of uncertainty, isn't it? Variances is a measure of uncertainty. Where are you? Okay, it's here somewhere. This one, let's take this. This refers to let me go here. This is the error in prediction. Okay. So what it means is error in prediction is always less than without prediction. That's what it means basically. Okay. If you use conditional expectations, is that good? Very, very important. Very important. That's the reason why we spend so much time in prediction using statistical methods. So we can see that as with our data. We saw this one already. Okay. The variance here, look at this one. The variance here is more than the variance here, isn't it? And each of them are more closer to the prediction, actual data.
Yes, sir.
So that is the whatever I explained before is actually explained before here, and then said here as a general principle. Again, I'm coming back and explained it. Yeah, you see that the variance here is less. This one, the blue is more closer to these people, which are male, and pink is more closer to this female data. Actually, this is, I'm going to put it as maybe a little bit more color towards pink, right? It's easier that way. Maybe let me put it as less pink, so that that it is referring to the pink, but not. It's different still from the average. Okay. And these two are male shape, right? Okay. These two are closer to the blue. Okay, little blue, lighter color blue. So the variance of this, the average, the variance of this is, the variance in the errors of this in general is less than the variance of all these four numbers. That's the main point. Okay, and so we all should be committed to do the modeling, predictive modeling, the way statistics is going to teach us and give us. And when I say statistics, remember, not really much different between statistical learning and the machine learning. Okay? Somehow they use what is called statistician use loss function. I will explain all those things. Loss functions and mathematical optimization. Machine learning people will use computer-based mathematical optimization, which means purely grind the computation, grind under what is called stochastic gradient approximation. Okay, but statisticians, use hardcore mathematics to get their work done. And where it doesn't give you, they still use numerical methods. But the point is, they will never use the level of sophistication that machine learning people don't need to do it. They don't want to do it. They have no time to do it. They have enough computing power to do it. Let the computer do it. That's the approach they take. There's nothing wrong with that. As long as things work, we are fine. Okay. So these are all things you can read yourself now. Let me go back to this height problem. Okay. One thing you should always do is when you get a data, make sure, can you figure out some patterns there? See, I said we have extra information about father side and mother side, right? Let's take just only one variable, father side. So height refers to child here, okay? Father means father side, height means child side. So because we are trying to predict, whatever we try to predict, we will put on the y-axis, the perpendicular axis. Okay? Whatever we are using as extra information, we will use it in the horizontal axis. So I wanted to take 5 minutes break, okay? And then we continue. We will finish actually doing a regression model yourself. Thank you very much. 5 minutes break. I'll pause.
Yes, sir.
Stop recording or pause recording. Again, it is available in one continuous file. You can always speed up and go back and listen to a few things. Why I said certain things and so on. So no worries. Take a good care. Be prepared. Don't worry about it. You'll be fine. Okay, and anybody attending my course should feel comfortable reaching out to Gaushali and me. Okay, so Gaushali is your, very committed advisor, mentor on student relationships, and we are all, every instructor is also committed to make sure that you learn and enjoy the learning, okay, and be the master you can be. So bye, happy Priya. Go, take care. Don't worry about it. So okay, let's go. Let's start. Let's continue. Okay. Bye. Take care. So what I was telling, okay, let me save this one because this is June 21 file. I want to save this. I make some changes here, so I need to keep that. I'll send this one, okay, later. Okay, got it. Now, let me go back to this, the presentation deck, okay. So the command ggplot, this command will get you this, okay, quickly. So what I do is context sensitive commands, and then the visualization I do a lot. So you are supposed to learn something, but you will learn more as we do these courses with me. Okay, and so here is the command I want to post it for you. Just you can copy and paste it, and you will get it exactly like what it got. Okay, as long as you did not change the name of the data set. The name of the data set for me is G. I use only one letter, okay, but refers to Galton data set. And then, so you can see, interesting thing is you can see this pattern, isn't it? As the age and as the father's height increases, the children height also increases. Do you see that overall pattern, Anto?
Yes, sir. I can.
You can see this way, right? It's going like this. So, today it is funny, and I read something very interesting, very beautiful question. I never heard that question before. That is such a wonderful question. Somebody asked me, so not asked me, I read it, somewhere. The question was, how do I find the derivative of a noisy data? Do you understand what I'm saying?
The derivative of a noisy data.
Noisy data, right. This is a noisy data, isn't it?
Yeah, too much
It's a noisy
unwanted
data.
information.
Huh?
A lot of unwanted information.
Yeah,
Irrelevant.
it's noisy. How do I find it? What is meant by derivative? First of all, derivative means rate of change. That's all it is.
Yes, sir.
How do you find rate of change here? You cannot, right? Our brain is going crazy. How am I going to find the rate of change? Which point I have to use to find the rate of change? Right?
Yes, sir.
But if I do this, I say, yeah, that is a crazy collection of points. I can't find the rate of change. Can I find the rate of change here?
Yeah, we express this as a line. Y is equal to mx plus.
If I express it as a line, don't even say it as a line. If I express it as some kind of a pattern in mathematical function form, then I can find the derivative.
Yes, sir.
That is the answer to the question. I can find derivative of a noisy data. This is the statement. Please write it down if you want. I can find
Yes, sir. Sure.
we can find the derivative of a noisy data if we can find the mathematical expression for the pattern of the data. And line is the simplest expression, isn't it? Because it could be, instead of line, it could be like this. I mean, the question is, does it fit that or not? This is the question, right? If this is the best pattern that fits the data, okay, fine. But if it doesn't, if it's not fitting the data, then the question is different, right? The answer is different. So the answer is, it doesn't fit in. The answer doesn't fit in. So the point is, if we can find a differentiable function, mathematical expression, mathematical function, then you can find the derivative. Is straight line differentiable? Of course, straight line differentiable, right? Y is equal to alpha plus beta x. Derivative of y with respect to x is beta. Correct? Do you remember?
Yes.
Yeah.
Yes, sir.
You are an engineer. So I talk more mathematics, but main point is, derivative refers to rate of change. So what it means is, as the height, the rate of change of height of father changes, what is the rate of change of height of children? That is the derivative. Please write it down if you want. That is also that statement. Okay, so I'm going to write it down. I thought that's an amazing question. See, that's what I'm telling you. That positions my explanation so easily to explain. No, how do we find derivative? A quick question, but it's a beautiful question. How to find, where is it?
I've written it down, so yes.
Okay, derivative use rate of change. Okay, so as the father's height changes, how much the children height change? That is what the derivative we are looking for here, right? But interestingly, the rate of change is for a line. The beauty of line, straight line, is that the derivative change doesn't change at all. It is the same at every point of the father's height, correct? It is the same beta. It is same the beta. Let me write down that alpha plus beta x, a plus bx is much easier for me to write. So this is the form y, height is equal to, height is equal to, this is what the equation is, right? I don't know something that's going on. I do that, but it's replacing something. Okay, so let me try one more time. I'll be very careful this time. So what I want to write is, this is height is equal to intercept plus, you said, you remember that, some ratio, multiplication by some ratio, you remember that, times
So which ratios?
You said
I
that
didn't
in
get
the beginning. I said, how will you predict? You said that. You remember? I'll take some ratio. You remember that?
yeah, multiplicative factor.
Multiplicative factor. Okay. Multiplicative. Let me write it. You know, I have something happened to my finger. That's why I'm getting to I have a tape here, and that's why I'm not able to put it. Type.
Oh.
Okay. Multiplicative.
It's all right, sir. I'll write it down. If you just could dictate it out, I'll write it down myself.
Okay, good. No, I think it's good to keep that here also. I think it's a good student question. I need to keep it and interpret it accordingly. Okay. You meant this. You said the same thing actually. And if you look at it, this is a straight line. Do you agree with me? This is a straight line
Yes.
formula. Alpha plus beta x or a plus bx. Okay. Or c plus mx. X is father side. Remember, father means father side. Height means children height. Okay. Intercept. So that is the simplest functional form you can derive out of the noisy data. And the derivative of this height with respect to father, that is x, right, is your rate of change. This is your multiplicative factor, is your rate of change. And that rate of change doesn't change, at any point. It's the same rate of change. As the father side, if you increase 1 unit, children height increases whatever the unit, it is same. That is why it is called multiplicative factor, single factor. So far, so good?
Yes, sir.
Okay, excellent. Now let's go into this. So I wanted to do a little bit of calculation here. I'm not going to spend time here. You can read this because basically I am trying to do the conditional expectation, conditional variance here. And because we know that conditional expectation is what is your best estimate, right? So for every father side, I'm finding the children's conditional expectation height. And not only that, how much variance is there? Conditional variance. You remember that I talked about conditional variance? So when the father's height is 62 inches, the children is also 62. Children conditional height is 62.3 inches. When father's height is 68.5 inches, children height is 67 point. Conditional expectation height is 67.4. So in life, instead of doing, what we are saying here is, if you randomly select somebody and use the additional information, what is the father's height, you will be able to give a more accurate conditional expectation values to the children, and they are more accurate. Okay, we saw those things, right? And that's exactly what I have done here. So you might question, why don't we just do this? Why do we have to predict? You just take this conditional expectations given the data and give that as the predicted values. You can do that. But there's a problem, right? There's too much calculation going on here, and you have to store too much information, isn't it? Instead of that, if I can just find this simple single line, how much information you have to store here? Not much, only 2 parameters. Okay?
Yes, sir.
Only 2 parameters. That is your intercept and your ratio, that multiplicative factor. Only those 2 parameters you will change. And you multiply whatever the randomly selected data, the father side, you use that to multiply that multiplicative factor, and then add to the intercept, you get the predictive height of the child. That is a lot more simpler than keeping this kind of conditional expectation. What if you have billions of not father side, but another problem, and we have, in a big data context, this could be a serious problem, right? There will be too many millions of, if not billions, millions of points of the x values. Here, x is father side. It's not a good idea, right? The better idea is, if I can use this simpler model, that is better. That is what the modeling is all about. And that is the simplest model is the linear model. This is what we are going to do. So we have a lot of, I have explained here a few other things, but let's just go ahead and do the modeling here quickly. So here what happens, I have done another version of the same thing here. So you can see one thing here, most of the averages, this is the average father side, okay? Most of the average, given the father side, most of the averages of the conditional averages of children's height is above whenever it is below this line, below this height, father side, okay, below this point. Above this point, the children height conditional expectations are below. Most of them are below. Do you see that one?
Yes, sir, I can see that.
You agree with me?
Yes, sir.
That's very important. That is what it means is it's not 100% true that as the father's height increases, children height always keeps increasing.
Yes, sir.
Bending this relationship, right? It is trying to balance two things. As the father's height increases, children height increases. As the father's height decreases, children height decreases. Also, it is centered around the father's height here in such a way that it is, it is not infinitely, it is increasing to infinity, because this is pulling that down. Okay, not all fathers with above average height will get above average children. That's, do you understand? That is called regression towards the mean. That's the meaning of the word regression. Regression towards the mean. It is regressing towards the mean. Do you understand that statement?
Yeah, I can get it. Somewhat I get, sir.
Yeah, but think about it. The point is, it doesn't, not all the fathers are going to get always higher children.
All the children.
And all the shorter fathers are going to get always a shorter children. No. So two factors are balancing here. Okay. That is, one is, of course, all fathers, taller fathers will get taller children, and shorter fathers will get shorter children. But also the other factor that is compressing towards the mean, regressing towards the mean is, all fathers, taller fathers will also get shorter children, and in fact, more shorter children. And shorter fathers will get more, taller children compared to their own height. That's what I'm saying. Understood? So they are coming, regressing towards the mean. That's where the word regression is coming. Okay. So if you use this command, you will get this graph. As I told you, there are too many calculations in all these conditional expectations. So it is better to find this single line to solve the problem. It's much easier to follow. So again, statistics is the science of approximation, best possible estimate or most likely estimate, and reducing the intelligence to fewer and fewer dimensions. Please write it down.
Yes, sir.
Excellent. So it comes down to fitting a line to these points. That's my conclusion. Fitting a line to this point. Of course, is that the only thing you can do? You can do nonlinear models, which means curved lines like a quadratic function or other nonlinear functions like polynomial functions and so on. We can do that, but this is the foundation. So let's fix the foundation more and more. So let's come out of that. We can run the model quickly. That regression model. I will come to that before the end of the class. We will come to that to the father's data. But let's understand. So basically, I said modeling is all about finding the best fit line. Finding the best fit line. So here I have 5 points. 1, 2, 3, 4, 5. Think about these things, okay? Anto, these 5 points, okay?
Yes, sir.
The point is a little bit more, but that's okay. We can move it back, okay? Like that, I can move it back. But the main point here is 1 point is here, 1 point is here, 1 point is here, 1 point is here, 1 point is there. 5 points are there, okay? Now the question I have is how do we find the best fit line? Okay, that's the question we have. And when the other thing is the line always has 2 points, 2 properties. One is it is intersecting somewhere the y-axis, and it has a slope, and the slope is same all over. Okay, slope refers to tangent of the angle it makes with the x-axis. Tangent of the angle it makes with the x-axis. It is same. This angle is same as here. Okay. If you have anywhere you draw a parallel x-axis, the angle is same. So how do we do that? That's what. Now visually take a look at this one. I'm sorry. Do you have a question?
No, sir.
Okay. So we are trying to find out the best fit line. The question I have is is the blue is best fit line or the red is the best fit line? Visually, just take a guess. Go.
Sir, I think it's the red one.
Why do you say that?
So although the 3 points fall directly on the blue line, but the point -2, 4 and yeah, the point -2, 4 has been completely ignored by the blue line. Like, it's quite too far. Like,
This
just
one,
from a
yeah,
visual point of view,
exactly,
I feel.
exactly. Excellent point. So you don't. It's not a question of how many points lie on the line, but it's a question of how many points are far away from the line. That is going to determine. Okay, because this is, of course, its contribution is 0, right? But its contribution here also very close to 0, very close to 0, very close to 0, right? They are very close to 0, but very far away from 0. This extra point distance will make it worse. Okay, this extra distance will make it worse. This extra distance. Okay, so in general, there is an optimization going on. What is that? The sum of squares of the total sum of squares of the errors should be minimum. That is the game. Whatever the line that minimizes the total error sum of squares. The error here is this error is 0 here, this error is 0 here, this error is 0 for blue line. But for red line, there's a small error here. There is a smaller error here compared to this one. There is a slightly bigger error here compared to this one. But then this error contribution is significantly more than anything you can imagine. As the error increases, its contributions is squared, right? It's exponentiated. As the errors increases, the errors are exponentiated. That's the main point. Okay, as the error increases, it's more and more contribution to the error. So you have to be minimizing the sum of squares of error is the best possible fit. That is what is called the loss function. I defined what is meant by loss function for you. What is the loss function? It is the sum of squares of errors. The one that minimizes the sum of squares of errors is the best fit line. You cannot beat that line. If sum of squares errors is the important loss function you want to minimize. Are you with me? Why sum of squares errors is minimization is the better thing? Because that gives certain better properties for the behavior of the model. I will leave it there, but we'll come back to that later. It gives certain better properties for the behavior of the model. Are you with me so far?
Yes, I'm here.
Excellent. Now, so kind of you can see that now. Why do I say the slope is 2? I already estimated that numerically. Kind of, right? Kind of. No, the intercept is 2.4 units. 1 unit, 2 units, 2.4 units. Are you with me? This is
Yes,
what
sir.
the intercept is. Okay. And the slope is 0.6. That means there is some angle to this one. See, 0.5 is this one. Actually, 0.5 refers to the 45 degrees, a little bit above 45 degrees. That's what we are saying. I'm kind of giving you some guesstimate here. Okay, so visually the best fit line seems blue, but then there is a problem. The best fit line is this one, because we are going to see it mathematically. So far so good?
Yes, sir.
Okay, now I want to jump one more important concept. Those 5 points, these are the 5 points. You see this one? These are the 5 points I wrote. And those 5 points are rewritten in matrix form. Okay, the first observation is corresponding to -2 is with the -4, 4 is with -2. The data points here, I'm writing it in this form. This refers to the intercept, and this is the x value, this is the y value, and then this model is -2 plus equal to plus a minus 4b plus error. Second is 4. This value is predictively, it can be written as a minus 2b plus error, like that. Okay. And this way of writing is what is called the matrix notation for this equation. And our purpose is to minimize this summation of 1 to 5 errors, error squares, not errors, error squares. And we want to minimize this. Whatever minimizes, we take the best model. Whatever that minimizes will give us the estimate of A and B. And that is our best model. Are you with me so far?
Okay. Yes, I'm here.
Excellent. So, this volume goes. Okay. So let me make it. This is already recorded now, but we'll come back to that. I mean, these are recorded individually because I want to convert this into later on video. So basically, what do I mean by error sum of squares? This is what error sum of squares means. Are you with me?
Yes, sir.
And if we use that, the 2.4 plus 2.4 plus 0.6 times x, this is what you will get as the errors. Each of these is the error, and then square them, you get the error is 20.75. Okay. Also, it looks like the slope is the tangent angle of the line with the x-axis. I talked to you about that. Okay. 45% means slope of the line is 1. If it is above 45%, 45 degrees, not percent. Okay. 48 degrees. It should be. It's not percent. Okay. Degrees. The intercept is clearly around 2 units. Around 2 units. Okay. It should be around 2 units. Let's do the model and verify these things. So everything is clear in this sheet for you?
Yes, sir.
Excellent. So I'm rewriting it in matrix form and equation form. Okay. Y1 is equal to a plus b x1 comma 1. That means in the matrix of data 1 1, it's not 0. It starts with 0. Think like that. Okay. This is x1 1. This is x1 2. Otherwise. Okay. So I can write each of these observation is written in this form, equation form, goes into this matrix form. Okay. And from there, the errors are calculated in this form. So minimizing the errors means this, and that's what I showed you as minimizing the errors. So far, so good. Anto?
So the last part, so we are minimizing that part. I couldn't get it.
No. So each equation I can write it like this. Each observation, can I write it like this?
Yes, sir.
Actual value is equal to structure plus error. Structure is the simplified model, best model that we are going to build. That is a structure.
Yes, sir.
Okay. So everything can be written as a structure plus error, structure plus error. And then in matrix notation, the same thing. Okay. And that results in the actual minus predicted, that is the error square, plus second observation actual minus second observation predicted square.
Yeah, I got it now, sir.
So sum of squares is minimizing. So we want to, this is a kind of differentiable function now. Okay. What is meant by differentiating noisy data? That's what this means. Now I can differentiate, right? Because I have structure here. Differentiate with respect to what? With respect to the unknowns, isn't it? Because we want to find out the unknowns. Unknown is not x1 and y1. It is unknown is m and c. Those are parameters. Okay. So I can use this. It's a quadratic equation, quadratic function, not equation, quadratic function. I can differentiate it with respect to m and c, get the answers. Okay, that's it. Problem is solved.
Yes.
Now, how do I get the answer here? Use this simple commands. I'm going to give you these commands and do this on your side, and let's see what you get. Momentarily, I'm giving you that. Okay. Copy and paste. You'll be fine. And tell me what you get.
So I haven't opened RStudio yet.
Okay. Never mind. I will run it for you. Okay. All right. Are you okay with me?
Yes, sir. Yeah. Next time I'll run it parallelly.
No problem. No problem. 1 second. Let me see. I have to move it here because I'm not seeing this stuff properly. Okay. Are you able to see now whatever I post? Okay.
I can see it.
Yeah. What if something happened because I still have these commands I should remove. Okay. Now you'll see the answer. Do you see this one? Very simple command, right? Summary LM, that means linear model. Y as a function of X. That's what R code is. As squiggle, tilde. Okay. Y tilde X means Y as a function of X, which means linear model. It's a linear model means alpha plus beta X or A plus MC. Okay. Or C plus MC type, right? I mean MX.
Yes.
Y is equal to C plus MX. That's what it is. So when I build the model, it immediately builds and tells me what are the errors here. For the best model, it found out. For the best model, the coefficient is 2 point. Intercept is 2.4, and now the slope is 0.6, and there are some bunch of values here. And there are more bunch of values here. Okay. Now, so what is the error sum of squares here? So can we do this one? Let me see. So I'm going to find out ln y squiggle x. Are you able to see the command, last command I'm typing?
Yes, I can see it. Residuals LM.
Residuals of lm of y squiggle x. So these are the residuals. We got it, right? I don't know what is it. Is the green coming to you, showing it to you, or what is this green? I think it is screen
Green?
sharing. Okay. No, nothing. Are you able to read these residuals here?
Yes, sir. 2.0, 2.8, minus 1.6,
Yeah. So
1.1,
let's do the sum of the residuals there, whatever I have. Okay. Sum of the squares of residuals, right? Sum of the squares of residuals. That's the beauty of R. Very easy to calculate. So 16 is the best reduced residual. Your residual error cannot go 16, isn't it? No, 10 or 16. Sorry. I can't read well here because there is a line going out around that. Okay, you know what I'm going to do. Okay, it's better. 16. Yeah, it is 16. Okay, you are able to see that?
Yeah, I can, sir.
Okay. So you cannot build a model reducing further than 16. That's the point. Okay. Now, there are some, there's lots of numbers here. I'm going to explain those things to you. Now, if you go back and see, let us consider that you sampled this data from some population, these 5 points. And if you go back and resample the 5 points, it may not be exactly the same point. In fact, it won't be exactly the same point. You agree with me?
Yes, sir.
And so if it's not going to be exactly the same, how reliable are these points, this estimate? That's a serious question, isn't it? I'm not going to get the same sample next time. So obviously this is not going to be 2.4 next time, and this is not going to be 0.6 next time. What am I going to do? How, then it basically, becomes a serious issue of credibility of the work or believability of the work. So what statistician found out is, now don't worry, we'll give you a formula that will explain all these things. Okay. So they said, they did some formula. I will show you those formula later. Okay. They developed a formula. They said, doesn't matter any time, any number of time you go and select it on an average. The estimate here is going to be only, this estimate minus this, comma, the interval of this estimate is going to be 1.3 to 3.5. Are you with me? So
yes, sir.
95% of the time, your estimate is going to be between those two. Well, not 95% of the time, but I think 66% of the time, because it's one standard error. If we do 2 standard errors, it is 0.2 to 4.6. Okay.
95%.
Yeah, exactly. So it's not going to be outside this most of the time. 0.2 to 4.6. That's a beautiful information. That's great information, isn't it? Because we have become very specific to an uncertain problem, right? And that is what this standard error will help you with. And instead of saying confidence level, you can say how reliable in a different way. That is what this p-value is. We can trust this. Instead of 90%, what we are saying is we can trust this with the 88%. 90% is better than 88%, isn't it? So the bigger the number here, it is bad, it's worse. It's highly unreliable. Smaller the number, it is highly reliable. So this one is 94%. This is 94% reliable. This is 88% reliable. Okay. So that is the way to interpret it. The higher the p-value, bad it is. The lower the p-value, it's better. Better reliability these estimates are. So far, so good.
Yes, sir.
So in addition to that, there are some symbols we use. So this means anything less than 0.1, 0.1, you'll put a star. Anything less than 0.05, you'll put a 1 star. That means it is 95%. This means 90%. And we don't like anything beyond 90%. This is not really, people don't like it. I don't mind, but 88% some people fall off. They don't like it too much. And if it is 0.01, that means it is highly reliable, 99% reliable. This means 1 in 1,000 reliable. It is almost reliable if it is 3 star. So we have a star system here about the reliability of these coefficients. Good, right?
Yes, sir.
Now you might wonder, okay, I'm fine with what happens if each one of them is some reliability level is there. Can you give overall reliability of the model? Okay. See, I have here not reliable at all. Here I have 90% reliable, and if I have another variable that is the 92%, the another variable is 97%, the another variable is 70%. Oh my goodness, there are so many different. I need one sentence. Is the model reliable or not overall? That's what this is all about. The rest of the information. Okay. The overall reliability of the model is given here with some values. We don't need to worry about these things, but again, go back to the p-value. This p-value says it is 95% reliable. It is the overall the model is reliable 90%. Do you understand what I'm saying?
Yes, sir.
Because no, I'm sorry. Is it the overall? This one is overall reliability is 90.
3.
Very close to 93%, right?
93.5.
Yeah, 93.5%. So it's 7% error is there. If it is below 0.05, then it is 90%. Okay, better, right? So it's okay. 93% is fine. I'm just telling you, it's not 95% reliable. Okay, because of this p-value, you have to interpret the p-value correctly. And then I also have, another important measure here. That is these two measures: multiple R square and adjusted R square. But we will come to the multiple R square. Always use adjusted R square because it adjusts for the number of parameters. This is a smaller model. It has only 2 parameters. If I have 10 variables into the model, then I have 21 parameters because each one has a derivative, incremental derivative, right? Incremental rate of change. And the instant constant is also there. So 20 plus 1 variable, 21 variables are there, 21 parameters are there. The more the number of parameters, you are making it more complex, away from simplicity.
Yes.
But the beauty of complexity is that you will be able to predict better. But the downside of complexity is that it becomes unreliable because more and more errors in prediction will be added to the prediction through various additional parameters. Okay, so adjusted R square is the best. So it adjusts for the number of parameters, also called regularity. We call it as regularization. I'll talk to you about regularization. Regularization is about adjusting for the parameters. Okay, adjusting for the complexity, same as saying complexity. Remember these words. Okay, so adjusted R square means this is very interesting.
Yes,
it says 63.96% of variance in the prediction is reduced by your method. I'm sorry. Let me say it again. I think I need to use the word right here. One word here. 63.96% of the total variance in the uncertainty of the outcome. 63.96% of the total variance. You remember I talked about conditional variance, total variance, error. Okay, 63.96% in the total variance, that is about the children height, is eliminated or explained by the father variable in using the father's height to predict the children height. So it reduces the total variance by 63%. Are you with me?
Yes, I was just noting it down.
Okay, that's very, very important. Okay, these are all interview questions. Okay, they will ask. So you understood all these things. So shall we do this for the other side and interpret the same thing now?
Sure, sir.
Okay, cool. Let's go to father side data. Let's probably should do some. Okay. So maybe okay, here. Let's do this. Here it is. Father side that here. I am writing it here. I can read all these things. So the main point here is, let's go back here and solve the problem. It should be some box plot. Okay. So I'm going to move this to here. It's better there. Okay. So, do you see this one? I'm basically doing the LM linear model formula. I don't have to put formula. It's okay. You can do just like this. But if you add data is equal to Galton, then you have to put the formula. Okay. Do you see what I'm saying? Is it too small? How about now? Okay.
I can see it, sir.
Okay. So the LM linear model, formula is equal to height squiggle dot tilde father comma data equal to Galton. I stored that object into LMG linear model Galton. Summary LMG, then it gives me the answer. It's also another way to do. Okay. You see here 3 stars are here. What does this mean? This means they are highly reliable, isn't it? That's what it means. Okay. And its p-value is very, very small. That's why it is the engineering notation automatically comes. Okay, this is a fascinating thing. Even though here there are, if you look at them, multiple R square, adjusted R square, it's only 6% or something like that, right? 7%. 7% of the children variance is explained. The children's height variance is explained by father side. But we'll come to that. There are ways to improve that. That's why this is a great example also. But intercept is this 39 inches. Are you with me? These are all now in inches. Every father's height, 1 inch height, is adding 0.4 inches height to children's height. Are you with me?
Yes, sir.
Excellent. And if you want to predict any children's height, you put this equation. This your multiplicative factor you mentioned is 0.39. Do you agree? That's your multiplicative factor.
Yes, sir.
Excellent. So children height is equal to 39.11039. That's coming here. Plus this is C plus MX. X is father's height. So when father's height is 70 inches, children height is just put to 70 inches here. You calculate this child height, and that turns out to be 67.06 inches, 7 inches. Okay. This is the way to build the model, one variable model, and interpret all the measures around this, and solve the problem. But here is the important extension I want to go after. Okay, this improvement is not good enough for me. Okay, there are issues there, so I'm going to do one small improvement. That is, can I add gender of the child? Because this refers to both in the average of both boys and girls, right? If you can separate the boys and girls, maybe it will do a better job. Okay, let's do that. It's somewhere here. Okay, here it is. Okay, so I'm going to move these 3 things there. I try to order these things in a certain way. So it's okay, we can keep here. So if you look at the same thing, same scatter plot, differentiate with a different color, you can do that using some color coding of the data. This is what happens. This is using without gender separation. The black is without gender separation. Anton, this is, it so happens all the boys are higher, right? Height than the girls, obviously. And then, so if I just separate out to the boys the height alone and then find their straight line, just visual straight line, right? Is this, and girls are here. So when I separate it out, your errors are going to be more, your errors are going to be reduced more. That means basically the more error reduction will happen, isn't it? I'm adding extra variable, that is gender of the child. When I do that, then you can see, for example, this is the adding LM data equal to G, formula is equal to height as a function of father plus factor gender. A variable which is qualitative is we called factor in R. So factor gender, I added additional variable now. Understand? Everything is great, significant. Look at this one, p values, everything is great. And then it's modified the formula here. Intercept is not anymore 33, 34.46. Father height is 0.42. And then gender is contributing. If it is a boy, add 5 inches. That's what it says. 5.17 inches. So when I do that, this is significantly improving the performance. Let's compare this, okay? Let's compare this. That is what is happening. This is the comparison equation. Are you with me? Are you able to see this one? Let me go there.
Yeah, I can see it. I can see it. No issues, sir.
So what I did is basically you might ask one question. One is, first of all, what is the performance of this model, right? The other one is, why don't we separate the data to the model? Let's compare that and see which is the best model. Are you with me?
Yes, sir.
Okay. So here I'm using the father's height. When I use the father's height, it is 7% error only with this, right? Now I used separately girls and boys. When I do that, R square is now adjusted R square is 21%. Where is this 7 and where is 21%? For who? For the girls. Okay. For the girls. For the boys, it is 15%. There is some difference, but nonetheless, it's much better than this, isn't it?
Yes, sir.
Okay. But if we do, instead of separating the gender, if we use the gender as a factor, what is the adjusted R square here? Look at this one.
60%.
Multiple R square. Adjusted R square is 60. Do you see this one? 60%, it explains 60% of the variance in the children height. Are you with me?
Yes, sir.
Okay, there are 4 numbers floating here. Adjusted R square without no inclusion of gender, 7%. Adjusted R square separating girls and boys, 21% and 15%. Explanation of the variance. But when I use them together in the same model, I get 60%. We are 10 times, very close to 10 times the original model.
Yes, right, sir.
That is the beauty of doing multiple regression, not separate regression. I want to stop here for today. And I will send this, and I want you to review, listen to this. There's a lot of material we compressed quickly in a very careful way.
Yes, sir.
Review this. Come back next time. We will expand on this. We will review this. Again, we will recall all those things. I'll ask this question. What are the most important 4 numbers when you compare the model? What is p-value? What is intercept? What is meant by finding a derivative of a noisy data? All these things we will review again. But we have come to an amazing result here. That is, if you do multiple regression, you cannot be beaten. So far, that's the best. We can continue to improve this also. Any questions you have? It's very close to 2 minutes to go.
As of now, none, sir. But when I go through these, if I have any doubts, I'll ask it out in the next session, sir.
Sounds good. Excellent. So my duty is to send this to you. I'll do that right away. And then I want you to review this, be prepared next week. You and Agripriya are buddies in the same class you've been, so please exchange information. Working with friends is very, very important. Because sometimes you will have a better reflection of the questions when you are becoming responsible to hear out or give input or ask with others of your class, of your nature. Okay, it's easy.
Yes, sir.
Thank you very much, Anto. Have a great rest of the day and rest of the week. I'm not sure when the lab is starting. Please keep in touch with Galton.
Sure, sir.
It will start pretty soon. I think after a few lessons because I'm prepping you right now. Thank you very much.
Okay, sir. Shall I leave, sir?
Yeah, you can. Bye. I'm going to stop recording.
Good day to you, sir. Bye, sir.
Good day. Thank you.